Hey guys, what's going on? Today I'm going to show you how to build neural networks from scratch using Python. So let's get started. What is a neural network? A neural network is simply a program which mimics the way the human brain learns in order to solve real-life problems. Examples include image recognition, audio recognition, speech recognition, etc. Now let's have a look at the structure of a neural network. So here we have these circle-like shapes which represent neurons, and each of these neurons holds different values. So we have these vertical stacks of neurons which are called layers. So the first layer is called the input layer, the last layer is called the output layer, and all the other layers which come in between, they're called the hidden layers. So in this simple example, you have only one hidden layer, but normally we can have more of these. And we have these lines which connect these neurons, they're called weights or edges. Now how does this really work? I'm going to be explaining this in different levels, starting from the most basic. So let's say, for example, I wanted to train my model to be able to identify whether a given image contains a cat or not. This would involve two different phases. The first phase would be the training phase, where I would train my neural network. So here I have my training data, which is a bunch of images, and each of these images has a associated label with it. A label can be 0 or it can be 1. A label of 0 means that the image does not contain a cat, and a label of 1 means that the image does contain a cat. The purpose of a label is to tell the neural network which image contains a cat, so it can hopefully pick up on its features and then learn to distinguish between which image contains a cat and which does not. So all of this training data is passed to our input layer. Then there's a forward pass, means the information is then passed forward to the hidden layer, where the information gets processed, and then it's passed forward to the output layer where we have our predicted values. Now these are probabilities. A value of 0.6 means that the neural network thinks that there's a 60% chance that this image contains a cat, and the second value, which corresponds to this image right here, value of 0.8 means that the neural network thinks that there's a 80% chance that this image contains a cat. These are our predicted values. Then we have the loss function, which gives us a measure of how well does our neural network perform. It does this by comparing our predicted values against the actual values, which are these right here. Okay, so using this information, we can then do a backward pass, meaning we can go backward from the output layer to the hidden layer. And what we're going to do is we're going to make changes to the hidden layer in such a way that the next time we compute our predicted values should be closer to the actual value. Now, what does this mean? So when we do backward pass and we make changes to the hidden layer, so the next time I go forward and I compute my predicted values, this value right here should be closer to the actual value, meaning it should be lesser than 0.6. And this value right here, 0.8, should be closer to 1, which is its actual value, meaning it should be higher than 0.8. Now this is called a backward pass. Now, this happens in many different cycles. We have a forward pass, where we pass in information, goes to the output layer, then we go backwards, we make changes, so hopefully we compute more accurate values next time. And we keep on repeating this until we have a loss which is minimum, meaning we have our accuracy as high as it can possibly be to ensure we have a well-performing model. Then we have the testing phase. This is where we evaluate the performance of our model to see if it actually works as we expect it to. This time we're going to pass in images, but we're not going to pass in any labels. We want our model to tell us whether this image contains a cat or not. And then we're going to pass this as input to the input layer. Then information gets passed forward. So there's a single forward pass, and in the output layer we're going to have our predicted values. A value of 1 means that the model thinks that there's a 100% chance that the image contains a cat, meaning it's fully confident. And then a value of 0.2 means that there's a 20% chance that the image contains a cat. Now I'm going to give a bit more detailed explanation as to how the neural networks work and what are the calculations that take place. So here we have a single neuron on the right, and we have these inputs on the left, x1 and x2. And we have these lines which connects each of these inputs to the neurons. We have W1 and W2. These are called weights. Now the purpose of these weights is to determine how much influence do these inputs have on the output of this neuron. So let's say, for example, W1 had a large value. It will mean that this input right here, x1, would have a large influence on the output of this neuron. And if W1 had a small value, it would mean that this input right here, X1, would have small influence on the output of this neuron. Now let's have a look at this neuron. It has two different parts. So this first part right here on the left, this is a linear function. So what this does is that it takes each of the inputs, X1 and X2, and multiplies them with the corresponding weights. So X1 gets multiplied by W1, X2 gets multiplied by W2, and we add all of them together. And finally, we add a small bias term. So let me show you what that looks like. So let's say, for example, we had a straight line like this. Y is equals to W1 times X1. So that's a straight line. So if we add a bias term to it, which is just a real number or constant value, it would have the effect of simply pushing it up vertically by some value. That's what a bias is for. And the values for these weights and biases, and for this bias right here, which is a small b, these are called parameters. Because these values keep changing, and the neural network is going to eventually learn these values, and it's going to keep updating them until we have the optimal values for these parameters. This is going to make more sense when I explain the backwards propagation step in a few minutes. For now, let's move to the next part. Then we have an activation function. This is called a sigmoid activation function. This is simply going to take the input from this linear function, the output from this linear function right here. After we do this calculation, and we get an output, which is this capital Z right here, I'm going to pass this as input to the activation function. This sigmoid function is going to give us a value between 1 and 0. Now, this activation function is normally used for the output layers because it's going to give us a value between 1 and 0. There's other kinds of activation functions. There's the value function, the softmax, etc. Now, the purpose of this activation function is to determine whether this neuron is going to fire or not. And most importantly, this activation function is going to give us a non-linear output. So it's going to take this linear output and it's going to convert it to a non-linear output. Now, this is very important. So let's say, for example, I did not use any activation functions, and I had a neural network which consisted of neurons which did not contain any activation functions. That would result in a final output of a straight line because I've just used linear functions. And that would be a problem. Let me explain why. So let's say hypothetically this diagram represented our training data, or the images which contain cats and images which do not contain cats. So let's say, for example, these blue dots represent images which contain cats, and these red dots represent images which do not contain cats. Now, it's not possible, it's very obvious, it's not possible to draw a single straight line that could separate these red and blue dots. So it can be solved with a linear, with just a straight line. Now, in order to solve this, we need to use an activation function, which will give us a nonlinear output. Therefore, it will allow us to learn these complex patterns or these features of our images in order to classify the images accurately. All right, so now let me give a full picture of how the neural networks work. So here we have the input layer, hidden layer, and the output layer. So as I said before, that each neuron has two different parts. It has a linear function and it has an activation function. Now this only applies to the hidden layer and the output layer. This does not apply to the input layer because the input layer just stores the input data, which is, in our case, it is the image data, which is the pixel values. So we're going to use images to train our neural network. And let's stick with the same example. We're trying to train our neural network to identify whether a given image contains a cat or not. So our image data is actually going to look like this, something like this. So we're going to have a bunch of images. They're going to be essentially matrices of pixel values. So it turns out we need to pre-process this data, meaning we need to convert this into a more neater form. So it makes it easier for us to train our neural network. So I'm going to be going more over this once we actually start coding our neural network. So for now, let's just assume we have our input data in the correct format. So along with the images, so we have three different images here. or let's call them 3 training samples. And then we also have our labels. So a label of 0 means that this is a not an image of a cat, and 1 means that this is an image of a cat. All right, another thing, we have parameters. These are the changing values. These values are going to keep changing throughout our training process. So we have parameters, we have W, which refers to the weights, and we have the biases. So what are weights? Weights are simply these connections, these lines, each of these lines which connect the inputs to the neurons, and these as well, these lines which are connecting these neurons, they're called weights. So each of these weights has a value associated with it. As I explained before, input really just determines how much influence does this input have on this neuron. Like how much influence do the inputs have on the output of the neurons. So these are weights. We have a lot of them. We have, I think, I'm not sure, around 20 or 10, something like that. So all of these are weights. And we have the biases. Biases are simply the small b in the linear function. So we have each neuron, I said before, has a linear function. So we multiply the weights times the inputs. We multiply, for each neuron, we're going to multiply these inputs. So let's say x1, x2, and x3. And let's say we're computing the linear function for this neuron right here. It has 3 connections. So W1, this is W2, and this is W3. So we're going to multiply all of these inputs times the corresponding weights, and then we're going to add a bias to it. That is the linear function for this neuron. And turns out all these neurons have this also going to have 2 different parts. This as well, and they all have the bias in them, this constant value. So these are also parameters. So each neuron is going to have a different b or different bias in the linear function, and that is set to random value. These are set to random values at first. So the parameters, they're set to random values at first, and these are going to keep changing throughout the training process. All right, so how do the calculations take place? So when we do a forward pass, we process each layer one by one. So this is a sequential process. So we're going to process this layer first, and then this layer. And how are the layers processed? So as I said before, neuron has 2 different parts. First, we're going to compute the linear function, which means that we're going to take all of these inputs, multiply them with the corresponding weights. So what are the corresponding weights? For this neuron, we have this line right here, this connection, and this connection. So multiply inputs times corresponding weights, add a bias to it. That's the linear function part. And then we have the activation function in the second part. So what is the activation function in the hidden layer? So we use something called a ReLU, rectified linear unit. So it looks something like this. Let me just draw it for you. Let's say this is a graph. This is the x-axis, and that is the y-axis. So ReLU function looks something like this. And let me write out the definition of the function. It is f of x is equals to max of x or 0. So what this means is that if we give it an input of any number, of any positive number that's greater than 0, we're going to get back an output of the same number. So for example, if I give an input of 5, I should get back an output of 5. If I give it a negative number as input that's less than 0, I'm going to get back an output of 0. Okay, that's the ReLU function, the ReLU activation function that's used in the hidden layer. The same thing is going to be repeated for all these other neurons. And the output for these neurons is going to be the output from the activation function. Let me just give it a label. So this one is going to have a 1 as the output after we apply the activation function. And for this, we're going to do the same thing. Take the inputs, multiply them with the corresponding weights. So these, they're going to be random values at first. The weights are going to be random values at first. And we're going to multiply them with the input, which is going to be our pixel data, our training data from our images. And then we're going to get some output from the activation function. Let me label it as A2. Same thing for here and all these other neurons. We have A3 and we have A4. So from this layer, we're going to get 4 different outputs from the 4 neurons. Now, what happens next is that all the outputs from this layer are now going to become inputs to the next layer. So we can see that this neuron right here has 4 different inputs. So it's going to take A1, A2, and A3, and A4 as inputs. So we're going to do the same thing here. This is going to have a linear function. It's going to do the same thing. Take all of these inputs, A1, A2, A3, and A4. We're going to multiply them with the corresponding weights. This is going to be W1. It's going to be some random value at first. W2, W3, W4. What we're going to do is we're going to take each of these, multiply them with the corresponding weights, add them all up together. So we're going to have A1 times W1 plus A2 times W2, A2 times W2, and so on. And we're also adding them all up together. In the end, we're going to add a bias to it. Again, this is going to be a random value at first. So this is going to be the output from the linear function over here, the output layer. And then finally, we have the activation function. So let me just do that over here. So the activation function that's used in the output layer is different from the hidden layers. So what we use something called the sigmoid function. Let me write it down. We have the sigmoid function. And what does that look like? Let me just show it to you. Let me just draw it out. So here we have a graph. This is the x-axis. And this is the y-axis. And the graph looks something like this. So what it does is that it takes, so this is 0. My bad. This is 0 here on the y-axis, and this is 1. So it simply takes an input of any number and it gives us back an output that is between 1 and 0. And the formula for that looks something like this. So the output is equals to 1 over 1 plus e to the power minus of x, which is the input. So this takes an input, gives us back an output that's between 1 and 0. So if you can see that if we pass in a very large value, so let's say, for example, 100 was our input, we can see that we're going to get an output that's close to 1, or it's 1. And if we pass in a very small number, let's say minus 100 was our input, which would be somewhere around here, you can see that our output is going to be 0 or close to 0. So this is the activation function that we use in the output layer. All right, so what we're going to get back is something like this. I'm calling it y hat. This is our predicted values. This is the output that we get from our output layer. This is like the final output. Not really the final output, because we're gonna be computing this again and again. For now, for the first forward pass, this is the output that we get from the output layer, and this is going to be some probabilities. So we have 3 of these, and why are there 3? Because we passed in 3 images. So what do these values mean? We have a value of 0.9. This just means that according to our neural network for now, it thinks that there's a 90% chance, or it's a 90% chance that this image is of a cat. 0.7 means it's 70% sure that this image is a cat. And 0.1 means that the neural network thinks that there's a 10% chance that this image contains a cat. So these are our predicted values. Okay, and what happens next? After we have the predicted values, we have a loss function. And what does a loss function do? A loss function simply tells us how wrong are our answers, or how far away are we from the actual answers. And there's many different kinds of loss functions. It really depends on what kind of problem you're trying to solve. So for this video, I'm going to be explaining what is the mean squared error. This is what we're going to use. The mean squared error, or MSE. What this does is that it takes the predicted values. Again, I call them y hat over here, y hat. And then predicted values minus the actual values. And what are the actual values? These right here. So predicted values minus the actual values, and we square them. That is the square error. And to get the mean square error, we just simply need to add them all up together, which in mathematical terms looks something like this. So M means our training examples. So all of our training, the loss for means that the loss for all of the training examples starting from here. So we're going to calculate the square loss for this, and this, and we're going to add them all up together. This is how we write in terms of a math equation. So, and we need the mean, so we're going to divide it by the number of samples, and we have 3 samples in this case. So let me explain this in a bit more detail, what this looks like. So let's actually go ahead and calculate what our loss is going to be for this example right here, which we just did. So according to the formula, we need to subtract the predicted value by the actual value. So what's that going to be? For the first sample, we have 0.9 minus 0.9 minus the actual value, which is 0 for this sample, for the first sample. Then we have the second. Also, we need to square it, right? We need to square the error. And then we have the second predicted value, which is 0.7. 0.7. And we need to subtract by its actual value, which is 0 for the second sample. And the third sample, I need to square it. And the third sample is 0.1. The predicted value is 0.1, subtracted by its actual value right here, which is 1. And then we need to square that. And to find the mean square error, we simply need to add all of these together. So this plus this plus this, and all of that divided by the number of samples. So how many samples do we have? We have 3 samples, so we're going to divide it by 3. So this is the mean squared error that we're going to get from the forward pass, after we do a forward pass. All right, so what happens after we calculate the loss function? If you were paying attention, you remember that I said, when I first explained about the neural networks, I said that when we calculate the loss function, we can use it to go back to the hidden layer, meaning we can do a backward pass and make adjustments to the hidden layer, such that next time when we do a forward pass and we compute our predicted value, it's going to be more accurate. Now, how does that work? Let me explain. Let's go along with this example when we first did the forward pass. When we first did the forward pass, I said that our parameters, which are the values for these weights, the values associated with these lines, and the biases in each of these neurons, they have different biases. These are all set to random values at first. And because they're set to random values, the first time we do a forward pass, our loss is going to be very high, meaning we are very far away from our correct answers. Our outputs are very inaccurate. That's what it means. And we can see that. So let's take the first training example. It has an actual value of 0, meaning it does not contain a cat. And according to our neural network, the output is 0.9, means it's 90% sure that the image contains a cat. And that is wrong. That is very wrong. So this is because of the parameters. The values of the parameters, they're set to random values at first. And these have an effect on what kind of output that we have, because we're doing all these calculations. And these have an effect on what kind of output that we get in our output layer. So in order to solve this, in order to get a more accurate output, what we need to do is we need to change these parameters the values for the weights and biases. We need to find a specific set of values for these parameters such that we need to find the optimal values for these parameters such that when we do a forward pass, we should get a very accurate output. And these values should be very generalized. What I mean by that is, so no matter what kind of images we pass in, or no matter how many images we pass in, the neural network should always be able to consistently give us correct answers. So if we give it an image of a cat, it should be able to give us an output that is hopefully 1 or close to 1. Okay, and how does that work? How do we find these optimal values? This is where gradient descent comes into play. Gradient descent is an algorithm that helps us find these optimal values. Now let me explain how it works. Alright, let's say we have a graph which looks like this. So on our y-axis we have the output of the loss function, and on the x-axis we have our parameter w. So if we were to plot the graph of loss, the output of the loss against our parameter w, we would get a curve which looks something like this. So what does this represent? This simply shows how much loss are we going to get for different values of our parameter w. So remember I said initially we're going to have a very high loss, let's say around 20, because we chose a random value for our parameter. And let's just say our value for w was 0.1. Now, what we need is we need to go down. We need our loss to be lesser. We need our loss to be 0 or close to 0. And we need to find the value of our parameter w for which we're going to have a minimum loss. So this is our goal. And how does gradient descent achieve this? This is done with the help of this formula. Let me just write it down. The new value of our parameter is equals to the old or the current value of the parameter w minus L. L is simply the learning rate, which is a constant value which determines how fast does the learning process take place. So let me just write it down. L, the capital L, is simply the learning rate, and we normally choose a small value like 0.1 or 0.01 for our learning rate. So let me just go ahead and use 0.1 for our learning rate, and then we multiply this by the slope of the curve at that point. So don't worry if this formula does not make sense. I'm going to explain what this is in just a bit. So how does gradient descent work? It simply keeps on updating the value of our parameter w until we reach the optimal value. The optimal value is the value where we have a loss that is minimum or close to 0, which is somewhere around here. Alright, so let me just walk you through an example of how this actually works. So let's say right now we're here. So our value for our parameter w is 0.1 and we have a loss of 20. So let's just use this formula. The new value for our parameter will be the current will be equals to the current value of the parameter, which is 0.1 over here, and we need to subtract it by the learning rate, which is 0.1 times the slope. Okay, how do we find the slope of the curve at that point? So what we do is we can just draw a line or a tangent like this, which touches the curve like this, and then we can just draw a small triangle, and then we can use this formula, height over width. So the height of the triangle over the width of the triangle. So that is how we find the slope of a curve at any point. Alright, so this part of the curve is actually pretty steep. This is the steepest part of the curve. So this is where our value for the slope is going to be pretty high. So let's just say it's 10. And it's actually going to be negative. and y negative? Because this line is going downwards. So you have a negative slope or negative gradient. So this simplifies to 0.1 minus 0.1 times minus 10 is minus 1. So we're subtracting 1. So 0.1 minus minus 1. So that will be, we have two minus signs, so minus minus will become plus, so it's 0.1 plus 1, which will be 1.1. Now let's just have a look at the graph to see if that's correct. Is that what we want? So we were here initially, and what we needed to do is in order to get a loss that is smaller, we need to push the value of the parameter w to the right. So if we push it to the right, means we're going to get a smaller loss. That is exactly what we're doing here. We're adding to the current value of a parameter, meaning we're pushing it to the right. Therefore, we're going to end up with a smaller loss. So 1.1, we go from 0.1 to 1.1. That is the new value of our parameter. Let's just say it's somewhere around here. This is 1.1. All right. Now let's just continue using the formula. So again, we apply the same formula again. So the new value of the parameter is equals to the old value of the parameter, or the current value of the parameter, minus the learning rate is 0.1 times the slope. And to find the slope, we just draw a tangent like this. At that point, then we'll draw a triangle, divide the height over the width, and then we will get the slope. And you will find that the slope at this point is going to be lesser than the slope over here. That is because this part of the curve is lesser steep compared to here. So let's just say we're going to get a value of 6. It's going to be minus 6 because it's going downwards. So this will simplify to 1.1 minus 0.6. Again, we have minus minus. We're trying to subtract a negative number from a positive number. That's going to have the effect of pushing the parameter to the right, and that is exactly what we want. So 1.1 plus 0.6, that will be 1.7. So we have moved to the right all the way to 1.7. We're at 1.7. So we can see we're getting closer to the optimal value. So we can apply the formula once again. The new value will be equals to the old value, or the current value, minus the learning rate times the slope of the function. To find the slope, we'll just draw a tangent. At that point, we draw a triangle, height over width, and notice that this part of the curve is even lesser steep. So the slope is now going to be even more smaller. So lesser, it's going to be lesser than 6. So let's just say around 3. So this is going to simplify to 1.7 minus 0.3, which will be equals to 2. So we're going to jump up all the way up to 2, which is our optimal. We've finally reached the optimal value. Okay, so this would even work even if we were on the other side. Let's say we were here. Let's say this was where we were at. This is our current value. Let's say it was 5. And to update the value of the parameter, we would use this formula. So new value of the parameter is equals to the current value, which is 5, minus the learning rate, which is 0.1, times the slope of the curve at that point. So we'll just draw a tangent like this. Again, we do the same thing, draw a triangle, height over width, that will give us the slope of the curve. Again, this is the steep part of the curve, so it's going to be a high value. Let's just say it's 9. And this time, it's going to be positive. We have a positive value for our slope. That is because the line is going upwards. The tangent is going upwards. So this is going to give us 5 minus 0.1 times 9, that is 0.9. We're going to get 4.1 as the new value for our parameter. Let's have a look at the graph to see if that's actually correct. So we are here currently. In order to get a more minimum loss or a smaller loss, we need to push the value of our parameter w to the left, meaning we need to decrease in value. And that is exactly what's happening over here. Because our slope was a positive value, we're subtracting this part right here, a positive number from positive number. That's always going to have the effect of pushing our parameter to the left side. So we're decreasing in value, meaning we're going towards this side. So now, after applying this step, we have value of our parameter as 4.1. And we can keep on repeating this until we eventually reach the optimal value. Alright. Another thing I want to point out about gradient descent is that when we're far away from the optimal point, like for example over here, we're going to take large steps. We need to take large steps. And when we are close to the optimal point, we need to take small steps. And this is achieved with the help of this formula because of the slope. So when we are far away from the optimal point, like let's say for here example, this part of the curve is pretty steep, so the slope is going to be a high value. It means we're going to either subtract or add if you're on the left side, it means we're going to always add because slope is going to be negative, meaning we're going to add a large value. If we're adding a large value, it means we're taking a large step. If we were on the right side, like let's say for here example, our gradient is going to be a large value, but it's going to be positive. And if it's positive, like over here, like over here, when we did this calculation, our gradient was positive. It was a large value. We ended up subtracting our current value, meaning we were pushing the value of the parameter to the left side to reach the optimal point. So we're going to take a large value when we are far away. We're going to take a large step when we are far away from the optimal point. And when we are close to the optimal point, our gradient is going to be smaller. Slope is going to be a smaller value. So we're going to shift by a smaller amount, meaning we're going to take a smaller step. And let's see why that's important. Let's say we're here, for example. And if we took a large step, we would just end up jumping across the optimal point. And then from here, we would jump again. We take a large jump. And we'll keep on repeating this. And maybe we might not even reach the optimal point. Or by the time we reach, we have taken a lot of steps. So this is why we need to take small steps when we're close to the optimal point. So we do this more efficiently.